Here we are with the mock extension final. Let's do the first section, which is about sequences and series. Okay, so this section is going to ask you to classify the sequence here. From looking at it, I do not see common step size going from one to the other. Like this step size would be -2 to 3. That would be step size of +5. If it was that pattern of adding 5 every time, then the next one should be 8, and it's not. Okay, so this is obviously not an arithmetic sequence. So let's try geometric sequence. That's the only other kind that we know. So going from -2 to 3, let's see. So I have the second term is equal to the first term times one number, which is called the common ratio. So if we have the second number being 3 and the first number being -2, what would be the common ratio? The common ratio would be 3 divided by -2, okay, which would be equal to -1.5. So if that's the case, -1.5, then we should be able to take -1.5 and multiply it times the second number, which is 3, and we should be able to get the next number. So 3 times -1.5, that is equal to, let's use the calculator. I know you're not supposed to use the calculator in this section, but just to show you that it's fine. -4.5, right? So 3 times -1.5 gives you -4.5. Okay, so this is a geometric sequence, and it's because I multiply by -1.5 to get the next term. Okay, all right. Explain how to find the common ratio difference as appropriate in this case, and then find it. Okay, so all you need to do is it's the common ratio, and we just take the second term and we divide it by, we take the second term and we make it equal to the first term times r, and so the common ratio is going to equal the second term divided by the first term. And the second term is -4.5. The first term is 3, so when we do that division, we get -1.5. Okay, so the explanation, you could say, first I divide the second term by the first term. And that's pretty much it. That's the procedure right there. Okay, for geometric. Okay. 1C. Demonstrate how to find the 10th term using the appropriate term formula. Okay, so you're going to look on your note sheet and you're going to have all the formulas there, right? So the formula for geometric sequence series is U10 is equal to U1 times R to the 10 minus 1. So that's the term formula. It tells you how to find the 10th term. So the first term we know is -2, right? And we know that the r value is -1.5. So from this information, we can figure easily the 10th term out. So we'll put -2 times r, which is -1.5, to the 9th power. Okay? Since this is a non-calculator test, you don't need to perform the calculation, just set up the formula. So we're just going to use that for the formula. Let's see, we're going to 1D. Demonstrate how to find the sum of the first 15 terms using the appropriate sum formula. So in this case, we're going to use the sum formula, which is S subscript n, and it's the sum formula for the geometric series. So it would be Sn equals U1 times 1 minus r to the n divided by 1 minus r. Put that in parentheses too, especially on the calculator, you need to put that in parentheses. So now let's be more specific. Let's say it's S15. So S15 is equal to, and the first term is negative 2, 1 minus, and we know the R value is negative 1.5. The N value is 15, and the bottom is 1 minus negative 1.5. Okay. Now we need a little bit more space, so shrink this down. Okay. So now, well, the only thing we can really simplify without the calculator is the denominator. 1 minus a negative 1.5 would be 2.5, so we'll change that to 2.5. And then the top, we can't really simplify because we can't really evaluate this without the calculator. The only thing we might do is we could take the negative sign out of this parentheses here. We could say, hey, we'll just, since this, we can take it out of the, because it's, if we multiply the negative sign times itself 15 times, it's going to be negative. So we could put it outside the parentheses, and since we put it outside the parentheses, we could just make this into a plus. Okay? In the end, we're going to have a negative out there anyway with the negative 2, right? So that's all you need to do. 1E, write an expression meaning the sum of the first 15 terms of the above sequence using sigma notation. Okay, so remember sigma notation. Sigma notation, you're going to have a sigma, and you're going to have a counter variable, and the counter variable is going to go from the first term, which is I equals 1, to the 15th term, which is the last term. And in here, you're going to put each term, which is, you could write it as the first term times the ratio times I minus 1. Okay? And we can substitute in that the U1 is actually negative 2, and the R variable is actually negative 1.5, right? Okay? So, let's see if this works. The first term would be I equals 1, so if you put that in, you would get negative 1.5 to the 1 minus 1, which is negative 1.5 to 0, which is 1, so it'd be negative 2 would be the first term. And the second term would be I equals 2, so it would be 2 minus 1 here, which is 1. You'd have negative 2 times negative 1.5, which is equal to positive 3, and so on. So yeah, it looks like it works. Okay, so what you're going to write is this expression here. Okay, all right. Does the sum, if infinite, diverge or converge? Explain what this means and justify. So, if you have a geometric series, and if R happens to be less than 1, or the absolute value of R happens to be less than 1, then like the values of the sequence slowly go down. And when it goes down like that, if you add up all those numbers together, you're going to approach one number instead of going to infinity. So basically the test is, well, is R less than 1? And if it is, that means that it converges. It converges to a number. Okay? In our case, what's R? R is negative 1.5. Absolute value of negative 1.5 is positive 1.5. Is 1.5 less than 1? No. So it diverges. Okay? So converges means the sum is a finite number, even though infinite number of terms. Okay? All right. Convert the repeating decimal 0.035353535 using the geometric sum formula. So the trick here is we're going to express this sequence as a sum, Okay, and so the first number is going to be 0.035, the first repeating part. And then I'm going to take the second repeating part and I'm going to add it here. It's going to be 0.00035. And the next one's going to be 0.0000035, and so on. Do you recognize that this sum on the right side, if it goes on forever, equals the left side? So if that's the case, then now we're going to make it look like a geometric series by multiplying times a number repeatedly on each term. So since we write it out like this, now we could say that, hey, U1 is equal to 0.035, R is equal to 0.01, right? Because this is the U2. In U2 we're going to multiply by R one time. In U3 we're going to multiply by R two times. So we got these two, and we have a formula which tells us that the sum, the infinite sum of a converging series is equal to U1 divided by 1 minus R. U1 in this case is 0.035. 1 minus R, it happens to be 0.99. 0.035 divided by 0.99. I could convert that to a fraction. I could say 35 divided by 990. Okay? And that was the whole point. Okay, we're convert the repeating to, oh, like in the instructions, I should have said to a fraction. To a fraction. Okay? All right. Let's go to page 2. So page 2 is about functions. We are going to take two functions, f of x equals 3x minus 3 and g of x equals 2x plus 1. And we're going to, first we're going to find the inverse function of the f function. Okay? We do that by doing a process called variable interchange. The way we do variable interchange is, first we just write out the, function out like this, and then we're going to exchange the x and the y positions. And then we're going to solve for y. So we're going to add 3 to both sides, and we're going to get 3y. Then we're going to say divide both sides by 3, and we're going to have x divided by 3 plus 1. Okay? So that's our function f inverse of x. So we could either say x divided by 3 plus 1, or you could say x plus 3 divided by 3. So the procedures are, you switch x and y, and then you solve for y. Okay, that's the procedure to find f inverse of x. Prove that your result is indeed the inverse of x. Okay, the way you prove that is you take the function and you composite it with the inverse function, and you show that that is equal to the original input. So what comes out is actually the input. And then you do the reverse direction and show that that is also x, and then you've proven it. Okay? So let's do that. We're going to take the 3x minus 3 function, and we're going to composite it with the 3x minus 3 function. Oh, I'm sorry. The 3x minus 3 function, and we're going to composite it with the x plus 3 divided by 3 function. Okay? So we're going to do that in both directions. So we're going to have 3x minus 3, and then we're going to put in x plus 3 divided by 3 inside. So this would be the, on the outside we have the regular function. On the inside we have the inverse function, right? So that would be this case here. And in this case, we can see that the 3's cancel out, and you're left with x plus 3, and then we subtract 3, and we just end up with x again, so it worked in that direction, okay? Now we're going to do the opposite direction, which is this direction. On this one, we're going to put the inverse function on the outside, so it's going to be x plus 3 divided by 3, and inside here, we're going to put the original function, which is 3x minus 3. We put 3x minus 3 in here, and then you can see that first thing that's going to happen is we're going to cancel out the negative 3 with the positive 3, and then on the top we're going to have 3x, and then it's divided by 3 on the bottom, and that is equal to x, and that has proven that in both directions, in this direction and in this direction, you just get the input back. So we have proven that the result is the inverse of f of x, okay? All right. Now we're going to take g follows f of x minus 1, and we're going to simplify it. Okay, so first thing is g's on the outside, so I'm going to write down g. So g is 2 something plus 1. Instead of the x, I wrote something. It makes it a little bit easier to imagine what you put in there. What are you going to put in there? You're going to put what's inside here, which is f of x minus 1. f of x is 3x minus 3, so I'm going to put 3 parentheses minus 3, because that is f, right? Now inside the parentheses for f, instead of putting x, I'm going to put x minus 1. Okay, now I have quite a complicated expression here. I'm just going to use algebra to simplify it, though. So I'm going to have 3x minus 3, because I expanded that part, and then minus 3 plus 1. Now I'm going to multiply out the 2, and I'm going to put these together. I'm going to get negative 6. So I have 2 3x minus 6 plus 1. Now I'm going to distribute the 2. I'm going to get 6x minus 12. 6x minus 12 plus 1 is equal to 6x minus 11. Okay? Okay, so our function g follows f of x minus 1 happens to be 6x minus 11. Okay. Give the domain and range of h of x and the domain of its inverse. Okay, h of x is this here. Let's figure out what the domain and range are for this function. So, if you look at the square root function, what can you put inside the square root function? What is the input to the square root function? The input to the square root function has to be 0 or more, right? Because you can't put a negative number inside the square root function. So the input here has to be greater than or equal to 0, right? What about the output of the square root function? The output of the square root function is always going to be a positive number, right? Because if you have a square root function, it implicitly means that it's a positive square root. Okay, to make it a positive or negative square root, you'd have to write plus or minus in front of it. So plus square root is the same thing as just having a square root with nothing written there. Okay, and so the output of a square root function is always going to be greater than or equal to 0 also. Okay, now what about this weird case where you have the square root of x minus 1? Okay, if you have the square root of x minus 1, that means the inside of the square root function, which is x minus 1, has to be greater than or equal to 0. So this is a little bit more complicated than just x is greater than or equal to 0. So x minus 1 is greater than or equal to 0. Let's add 1 to both sides and see what we get. We get x is greater than or equal to 1. Okay, so this is our domain for this function, square root of x minus 1. So the domain is x is greater than or equal to 1. That's the domain. Okay, what's the range? Well, we know that the range is going to be greater than or equal to 0. Okay, so the range of the h of x function is going to be y is greater than or equal to 0. Okay, let's see if those match up. We're going to take the smallest domain value, which is x equals 1. We're going to put it into the square root of x minus 1 and see what we get out. We're going to get square root of 1 minus 1 is equal to the square root of 0, which is equal to 0. And that turns out to be the smallest value of the range. So that worked out. Okay. The other way you could do it is you could create an XY table. Okay, so you're going to say, oh, I'm going to create an XY table. I'm going to put in some numbers in here like -1, 0, 1, 2. See what I get when I put them in. So if I put -1 in there, -1 minus 1 is -2. Take the square root of -2. That's illegal. Okay, then I put 0 in there. 0 minus 1 is -1. Square root of -1 is illegal. Okay, then I'm going to put 1 in there. 1 minus 1 is 0. Square root of 0 is 0, so that's my first valid value. If I put 2 in there, it's 2 minus 1 square root, which is 1 square root of 1, which is also 1. Okay, and then it continues to go on there from there. So then, looking at this result, it looks like, oh, okay, looks like the domain and the range kind of start at x equals 1 and y equals 0. So you can get the same answer by making an XY table or sketching the graph or something like that. Okay? All right. So, and then, so we gave the domain range of h of x. This would be these two here. Okay. Now we're going to give the domain of its inverse function. Okay. So the domain of the inverse function, remember, is going to be the range of the original function. So this is for h of x. Oops. This is for h of x, right? So the range of h of x is equal to y is greater than or equal to 0. So the domain of h inverse of x has to be x is greater than or equal to 0. Okay? And the reason why that works is because when you find the inverse function, you invert it, or you reflect it over the y equals x line. So the y becomes x and the x becomes y. That's why variable interchange works. Okay? All right. Next section, trigonometry. We'll do that on the next video.